And yeah, this week, Thursday, 2 days from now. And I mean, probably I'll send you a Zoom if it's all materialized, but it looks like most chances. And a Zoom, we prepare for you a recorded lecture. Let's talk about homework 3. So in homework 3, you have to implement a ray tracer, at which you'll have as an input a JSON file. JSON is kind of a language that allows you to define objects. Probably have seen it before. If not, the syntax is A, very easy, and B will give you a reader for it, and it will generate an array of spheres, balls, and it will generate an array of list of billboards. This is one billboard, this will be another one, and it will tell you where should you put the camera and what the camera parameters. And you, as a return, will produce a frame when it's just a single frame, or a video. We'll ask you to generate a few videos when the angle of the camera or the location of the camera changes. And we'll figure most of the math today, and a few minor details will stay for Thursday. But that's a type of that's a type of videos that you can generate. I mean, I insist on the video here so you can see how the things, what are each billboard. Billboard is what you think about billboard that you see on the road, like a commercial billboard that you put a big image on it, and we'll just give you a few images here of a cartoon, your favorite bunny, some background. Over here, there are a few spheres. On these spheres right now, there is some shading that involves where the light is coming from and what is the dark side of every sphere that you don't need to implement in homework 3. It will wait with other thing for homework 4 and later. Things, the shading effect of each sphere are waiting, but where the camera is and what do you see on each pixel, that a pixel that you shot through from the camera to the wall hits the billboard, and then you'll go to the file that contains, or to the area that contains this billboard, figure out, oh, in this billboard, I know what the coordinates that my ray hits this billboard, so I can figure out what is the color of the billboard. It's this pixel, and that's what your camera will show as a pixel on the camera screen. Lot of terminologies that we'll be familiar with, all of it very soon. Okay, so homework 3 is to produce this type of videos. And why do I make such a big deal with billboard? So billboards are really, really important in computer graphics, particular interactive computer graphics. Extremely important. Like what? We can take an object like a sphere and put some texture on it. This texture might repeat itself. We can say, oh, this looks like the floor over here, so there is a carpet, and this carpet has a pattern that repeats itself. Obviously, we don't need to put all the whole carpet, but it's essentially the same pattern that appeared multiple times on this big plane. So it's related to texture of the object, a way for us to make the object look like it is fairy, or it makes of wood, or it's completely flat and shiny. It's all involved, the texture of the object. But more maybe, not less. Common usage, especially if you are in interactive computer graphics, where the user, that is the player, the camera, moves, or I'm looking at this direction, I'm looking at this direction, zoom in, zoom out, changing the direction of my head, that is rotation, if I'm flying, changing my orientation in space. All of it I need to do in frame rate time. And to do it, what I'll do is not to do the whole ray tracing for each individual frame. As we'll see, it is extremely time costly. Even when we are using hardware to do a lot of the ray tracing in parallel, it's still very costly. We'll see why, because it's need to be actually, to get the right effect, it need actually to be recursive in some sense, so the computational burden is really intolerable. Instead, what we'll do is look at what happened to the chairs over between there when I'm just moving a bit to the left, a bit to the right. Well, if the chairs are very close to me, then one chair will occlude the other. And I need to tell the user that one of them now moves with respect to the other. And if I will not show it to the user, it will be very annoying. What happened to the chairs that are much further away from me? If I'm over here or I'm over here, the chairs in the background did not change much. Definitely is not, they didn't start to partially occlude each other or not, which would make it very obvious to the user that I'm cheating or not, if one should occlude the other or not. What happened is that mostly the background, and we'll talk about it much more, stays static as the user moves. The big mountains that are far away from you, you don't expect one peak to start occluding one peak unless you fly all the way to far, far away from where you start, which means we can look at the three-dimensional data that we have for everything in the background, spend pre-processing time, create one image that will live in the background, and put it on a big billboard. So the big mountain in the background are in the background on one billboard that will stay pretty much static. And everything that happens closer to the user, well, we'll have to spend the time to show it explicitly. So we are combining the three-dimensional rendering would consist of object in the background that we just show a billboard that looks like how the mountain should look like, but that's pretty much static, not entirely, and nor the billboard will not entirely static. There will be changes in them that happens implicitly because of what we'll call homography. We'll talk about it more. But so there is some changes, which is absolutely fine, but there is no relative changes of the position, which would obviously trigger the user to realize we are cheating over here. Enough to put one big image in the billboard, and later on we'll also study how, and at this point of the course, you'll have to do it in the slow way of ray tracing. Later on we'll see how WebGL and OpenGL and all the hardware parts can support like environmental rendering, where you'll just say, whatever the user see in the whole room consists of 6 images of the cube surrounding me, and I'll just give them as 6 separate images, and then when the user change the direction of the camera, I'll be able to show the background. Same goes with trees. Trees is a good example, very complicated thing. I don't want to render each individual leaf in real time. Of course, think about game planning, everything with game design. I don't want to think about the trees as really three-dimensional object. What I'll do instead, I'll put every tree on its own billboard. I'll put a billboard with a picture of the tree. But now there is a problem. If I put a billboard, which is a rectangular thing, let's see, it's either a triangle or rectangular thing. In your homework, it will be always a rectangle. One billboard, and now that's one tree drawing on this one, and another one with another tree. Well, this billboard will occlude this board. Well, you see that you can see 2 trees over here, one after the other. So how come we create one billboard that will not necessarily occlude the other? See? This tree occludes the one in the background, as we want. But if I put the first billboard on a rectangle, it will occlude the whole rectangle behind it. So how come we see the 2 trees at the same time? Help? Everything that is not leaf specifically specify as transparent pixel. So a ray that hits a billboard but hits a transparent pixel just keeps going until it will hit a leaf of a tree that do exist. Okay? So that's where, you do need to implement also. In the homework, you are getting RGB alpha. Alpha transparency. We'll just use in this homework alpha, which is either 1 to 55, or 0, completely opaque or completely transparent. Make sense? Now, in general, for the same tree, it's not that we store we said we pre-process an image of the three-dimensional object of the tree, and that's done in the pre-processing. Pre-processing, taking the three-dimensional tree and make a two-dimensional image of it. What's not true is that we are always happy with just one image, because then changes of the tree, one leaf, one shred of the tree occludes the other one, will be very obvious, and that's why we need to prepare multiple images of the same tree from different angles. And sometimes we'll break the tree into sub-pieces of the trees out there. Anyhow, that's why I'm putting so much importance on a billboard, also known as imposers. Right? It makes sense, right? That we have one billboard that imposed for being a three-dimensional scene. So that's about the homework. And from now on, it will just be a format of how can I get a set of objects, start with a set of spheres, all live in three-dimensional, and camera parameters. Where are the camera located? And what is the camera looking at? What's the angle of the camera? And so on, list of parameters of the camera. And out of it, I'll be able to render an image of, well, the forest in this case. So from this point, it just starts to be the math of how do I do the ray tracing and what is ray tracing at all. Any questions so far? So your bits or pieces of math that you need to do all the homework. So we discussed dot product last meeting. We started to discuss cross product between vectors. So cross product, we can define it geometrically. I have two vectors, A and B, in 3D. I'll create a new vector called A cross B. Now, it's not true that A cross B equals to B cross A. Sometimes it's true, but not always. So A cross B and B cross A might be different vectors. What is a new vector that I generate? It's orthogonal to both A and B, and so it's orthogonal to both these vectors. So it's a normal to the plane that A and B defines. Every two vectors that are not parallel to each other define some plane, and A cross B is orthogonal to this plane. What's the length of A cross B? Well, it's the area of this parallelogram, which also known as the length of this guy times the length of this guy times sinus this angle. Okay? So for given A and B, the maximum length will be if they are orthogonal to each other. So quite the opposite of dot product, where dot product, if I have two vectors that are orthogonal to each other, their dot product is 0. For the cross product, I maximize the length. So I told you what's the length. I told you about at which direction it goes, modulus that it can go downward or upward. Well, here comes the right-hand tools. If that's A, that's B, then C points on this direction, on your right hand. Not the hand with the watch, the other one, okay? A, B, C will point in this direction.
I do what I want with the right hand, though. I do what I want with the right hand. You can't say
that. Okay, rules about it. A times B cross C. Everything all behaves almost as any normal multiplication, except that you cannot change order. Again, A cross B and B cross A are different. And B cross A, right-hand rule, B times A, if this finger is B and this finger is A, then think about the screw. I'm going from B to A, which direction the screw wheel goes, normal screw, it will penetrate downward. Right, the opposite of this one. So A cross B and B cross A are going in opposite directions. Sorry. And there is a formula for what is this vector. A cross B, it has 3 components, x, y, and z. Of course, if you are using homogeneous coordinates, then you're just putting 1 normally at the end. And here is the x component, here is a y component, and here is a z component, which is, let's meditate a bit more on the z. It takes the x parameter of the first vector times the y parameter of the second one, minus y of A times x of B. And Z is a bit more important. You'll use it multiple times in this course about this one. Why is it so important for us when we are generating in this course? Why are we using cross product all over the place? Well, because I'll tell you to start that here is my camera. That's the center is its location. I'll also tell you about one vector, which is the center of attention, the direction that from the camera I'm looking at the center. Many more figures to come about it, which direction it comes. But that by itself doesn't tell me. Think about here that's a camera is pointing this way, that's a camera, and that's the image that I'm going to render about everything that happens over here. So I'm going to shoot rays through the camera, and they are going to hit in this direction. So I told you where the camera is. I told you what is the direction, which is, mind you, one of the vectors that I defined here. I also need to tell you what is the up direction. I have a lot of options to tell you what is up, but up is roughly where my head is pointing to. That is, usually it will go vertically up unless you want to draw, and there is flight simulation, and in your flight simulation, you want to rotate, which is how do you implement it. In the videos, you're just changing the direction of the up vector. Now, I'm not committing the up and the look at. Vectors are orthogonal to each other. It's quite convenient to keep them separate from each other. Up is up. My attention focus can be changed in this direction up and down, but up stays the same. So I'm going to create as a direction where I'm drawing my image, and the way I'll do it is ask, I have the up direction and I have the direction that I'm looking at. What will be my right-hand direction? It should be, my right-hand direction should be what? It's orthogonal to the direction that I'm looking at. I'm looking over here. My right hand is orthogonal to this direction, and it's also orthogonal to the up direction. So now I'll take the look at and the up, do the cross product. This gives me the right direction. I'm missing one more direction, one more vector, which is what I just created in the image would be the horizontal direction. The horizontal image of the direction is what I just created, the cross product of the down and up. Plenty more to come. I'm just giving you motivation about why cross product. So I created one cross product to discover what is a horizontal direction. Horizontal as far as the camera is concerned. The camera might be tilted, but as far as the camera is concerned, that's a horizontal direction. How do I create now the vertical direction of the camera, which might be or might not be the vertical in your world, the z direction, not necessarily. How do I create this one? Well, I have already one direction where I'm looking at. I built the right direction by one cross product operation. Now I'll do the cross product of these two directions. It will give me the third direction of the camera. Plenty more of explanation to come. Okay, so I need it to build my coordinate system. Playing a bit more with, sorry, and why do I need the coordinate system of the camera? Because now I can determine about a set of rays. I'll tell you what is a ray algebraically. Once I determine what is a ray, I can ask, hey, this ray, what are the objects that you are hitting? At which time are you hitting ray? At which time are you hitting each one of the objects that you are penetrating? Let's find the closest to us, and let's take its color, and that's the color that we are going to assign to this ray. That is, to the pixel that was generating the ray. Okay. Quick examples. If x is 1, 0, 0, y is 0, 1, 0, and z is what you think, then x cross y is z. Okay. And y cross x, switch the order, is minus z. Let's talk about one of the first questions that everybody that do game everything asks. Here is my image, x and y. That's the image, and I'm asking where are the objects. I want where are the objects. If I want the z direction to be a normal right hand, but right hand will tell me that x cross y, and x, y, z, x, y, z goes in your direction. You're the viewers. Where are the objects that you are viewing at? On the other side of this wall, with negative z. Remember the one paradox? Everybody asks, why do I have to make it so that if an object is very far from me, then its z value is very small. It's a negative number. If you're watching on an object, now z would be the depth, and let's just draw the x value. This is a z, then objects, then, so if that's a z, this is the z, then for the same x, if I want to draw object A that is behind object B, then both of them has negative value, and this would be, say, minus 20, while B will be z equals minus 10. Why? Now you understand. Because we want to map the x, y, z to right-hand coordinate system that we know normally, which will impose that the viewer is in positive z, and the objects are in negative z, and the further it is from you, the lower its z value. Make sense? Because we want to be able to switch one coordinate system to the other by just align them one on top of the other. Now, let's your graphic machines like triangles most of the time. And triangles, I'll send your monitor 3 points, A, B, and C. And I want, and so your monitor gets the location of A, B, and C, these 3 points. And your monitor needs to decide, should I render this triangle or not? And one of the ways to know if you should know it or not is what's called back face culling. If this triangle is part of a big object, but this object is opaque, then a triangle that I'll draw on this side of this cylinder, you should not worry about rendering it because it's occluded by this side. A triangle that is facing me is occluded by this side. But how can I know if the triangle is facing me or facing the other direction? The vertices are the same. Well, trick, we'll always keep the agreement that when I'll tell you about every triangle, its No, if I'll tell you, if you're watching the triangle, if the triangle is facing you, then I'll report the 3 vertices in counterclockwise order. So it should be actually, if I'll tell you about the 3 vertices, A, B, C, and I'll tell you about them in counterclockwise order, from A to B to C, walking along the triangle in counterclockwise, it means you're facing the triangle. If you see the same 3 triangles, but if you watch as the very same triangle, but from the other side of the wall, you'll see that A and C now, it is put on it from the other direction. You'll still see A, B, and C, but from your other side, it goes in clockwise direction. Fine. So now I want a really quick way to check for 3 numbers if they are appearing 3 vertices, 3 points on the plane. Do I get them in clockwise or in counterclockwise? Or, God forbid, they are actually collinear. I want a quick way to check it. Let's go back a few slides. What is the length of this vector? Based on the agreement that the length of this vector is the area of this parallelogram. Based on this agreement, if the 2 vectors are collinear, what is the length of A cross product B? Just go geometry. It's the area of this parallelogram. What is this area if they are parallel to each other? It's 0. All agree? The length of this vector must be 0 if the area of this parallelogram is 0, which happens if and only if A and B are pointing in the same direction, or actually if they are opposite to each other, or the other case. But they are living in the same line. Looking at the big formula that I had before, it just boils down to asking if this expression xa minus yb minus ya xb is this larger than 0, at which you'll understand that the vertices UVW are, if this expression, the z component from the slide that we had before, the big scary expression, if UVW are given to you in a counterclockwise order. Ooh. Yeah. ADHD, sorry. I wish that I can say that I've never done it before, but yeah, if I'll give you the vertices, let's just stick to the slide. If I'll tell you about the vertices in counterclockwise order, then this expression is positive. If it's negative, it means that this, I tell you about the 3 vertices in clockwise, meaning the triangle is facing away from me. How do I know it? Because I'll decide that the normal is not only orthogonal to the plane that contains the triangle, but actually I'll define the unique normal as it's going based on the cross product. The normal is a single one that points to the cross product, and if the normal points away from me, then it means the normal to this object is pointing away from the object, just as an agreement. We all agree about it. That's how you sieve your data, and that's how you can cull a few triangles, not to render them, because you'll figure out that you are just watching them from the back face. So there should be another triangle. So I tell you, if it's counterclockwise, normal toward you. You're facing the triangle. You need to render them. You see this triangle. At least maybe it's occluded by other objects, but at least it's not occluded by the object that contains this triangle. These 3 vertices are, if the z component, this expression, negative, it means you're getting them in clockwise order. Yeah, clockwise. order. And what's left, if it's neither positive nor negative, equals to 0, then the two vectors are pointing in the same direction or opposite to each other. This triangle has 0 area. Okay, so quick and easy way to check what it is. Now, of course, we'll give you a code for the cross product. It's just about, in GeoGebra and in most languages, you're giving two vectors, just writing cross of both of them, and it will spit out the results. Didn't find it very fascinating to implement it. So we'll give you the code for it. Why did I do it? I don't know. Let's talk about ways. I have a few vectors that you see right here. To see a vector that I called v times x, it's a vector 1, 0. A unit vector that points in the positive x direction. Similarly is vy. And here is another vector v. Another vector v that points somewhere. And I'll make sure that this vector is a unit vector. Not hard to correct it, but let's assume that this vector is a unit vector. V is a unit vector as well. And now I want to take this vector and multiply it by the scalar. Multiply by a scalar, just to remind you, is t times x of v, comma, t times y of v. X of v, y of z are the components of v. And t times z if it lives in 3D, as your vectors will be. So this is a vector v. I'll tell you that this is a unit vector. How can I do it? I'll make sure that I'll set v equals to v vector, new v, equals to v vector divided by the length of v. V divided by the length of v will guarantee what is division. It's multiplication by the scalar 1 over the length of v, the length of v. And now I'm sure that the length of v is 1, what we call unit vector. And now I'm looking at all the points, all the vectors that I can generate by taking v and multiply it by a scalar t for time. If I'll just multiply it by only negative t, then v times 1 is just v itself. V times 2 is a point, a vector that is just twice as long. V times 3, 3 times as long. And as I let v goes up and down, I'll increase t. And you see the point r, which is t times v, the current value of t times the length of v. This is this new point r. What is a line that contains, what is a line that v defines? How can I generate the line that we defined? So far, I just generated the ray that emerges from the origin, the line that starts at the origin and continues in the v direction. How can I generate the other ray? I'll just let t be any real number. Positive will be Positive number will be only the array. Positive and negative are all the lines that it contains. So now you know what is an array that emerges from 0, 0. Here's V as in the GeoGebra. And here is a point O1. And I'm looking at O1, this point, plus T times V for all the T's which are positive. What is it? Help? Where are all the points? O1 is 1 point. Where are all the points that I generated by letting T slide from 0 to whichever number? But these are all the takes this way and put it parallel to itself. Just put it here. Make sense? I just shifted the array so it starts at 01 instead of starting at 0, 0. And now I like this example because it is a very useful trick that we'll use a lot here, but it's what I'm going to ask you is how do I find the projection of some point P, and I want to find its orthogonal projection of this ray, where I started to explain it last time in a very pathetic way. So let's try to do it better. So I want to find what is a point which is the orthogonal projection of P on this ray. And the way algorithmically that we're going to do it will be identical to the way that we'll find intersection of the ray of other geometric objects. Instead of thinking about a ray as a static infinite set of points, we'll think about a ray as something dynamic, changing in time, and we'll just ask at which time did we just hit this desired point where P, think about the point R. Its location is a function of time. I'm slowly increasing R, and at some point, I just noticed that I just pass through a point P prime. What is P prime? The orthogonal projection of P on the line. Okay. I'm letting T varies. When T was 0, I'm back to the case that OO is 0. Otherwise, the changes are very minor if it emerges from O1 instead of 0, 0. So I start shooting the ray from 0, 0, and I look at the angle between the points that I'm currently at. R is T times V. Here is R larger. That's where I'm right now. And I'm looking at the angle that R generates between the line I'm coming from, and I keep staring at P. And what do I ask? What is a big difference between this T, which is obviously too large, T, which is 2.78 seconds, don't know, versus T, which is too small, like so, and look at this angle. Now this angle is larger than 90. Yeah. Now this angle is smaller than 80. I'm looking for a time at which this angle is exactly 90. Make sense? That's the orthogonal projection. The point P prime that creates angle of 90, that's the closest point to P. That's the orthogonal projection. And you'll use it a few times in homework 3 when you'll ask, I just have a point and I want to ask where this point is in the image in the billboard. How can I represent this point on the billboard? And you'll see that it's very easy. So what do I do? Checking this angle and saying, I want to stop at some time, T0, at which this angle, the angle that you see right here is exactly 0. What happens when this angle is 0? Well, it happens for some time, t0. What is the point r at this time? R is just t0 scalar times the vector v. What do I want it to be at this very specific time t0? It should be orthogonal to the vector that connect p with r. At this very moment where p is a function of time going through p prime, the projection, this angle is exactly 90 degrees. Look at this angle. The angle between the vector connecting p to r and the angle of t times v, voila, that should be 90 degrees. P minus, what do I have t times v? That's r. What is p minus tv? It's this vector, h. What is this vector? T times v, this direction. They should be equal to, they should be orthogonal to each other. Orthogonal to each other, what is a dot product? Dot product is the length of this vector times the length of this vector times cosine. Cosine is 0 when the angle is 90 degrees. Dot product is 0. That is, this guy times this guy, these two vectors, the dot product should give me 0. Let's write it down. T0 times v, dot product with v, should be equals to, taking this part to the other side, t0 times v times t0 times v, which is t0 squared times v times v. What is v times v? Not always, but I told you that I'll make sure that, help, what is v times v? V times v is 1 because I made sure that v times v is that v is unit length. The length of v is square is nothing but v dot product v again. Right? Just Pythagoras. So this is 1. What are we getting for? T times v e cubed times p equals t square. In this point, it looks like a quadratic equation, but it's not because I have t0 here and t0 here. When we'll talk about spheres, you will have to solve quadratic equations to see where the way hits a sphere. This is simpler condition. I'm just getting so close to p. So divide both sides by t0, and you're getting to that t0, everything that is left here, is just p times v. And that's it. So that's how I found the time, which is algorithmically how you'll always work. And once you find the time, you can actually ask, what is a point p prime? What is there for p prime? It's the time, which is p times v. That's a scalar times v. Sanity check. Here is a point x, y. That's a point, a different point, q, x, y. Please tell me what is the closest point along the x-axis. What is the closest point to q on the x-axis? You all know it, but use this form. What is this way? The positive axis is, first, x as a vector, what we call vx. It is a vector 0, 1. 0, what? So this ray is t times, I can just call it t times vx. Here is q. What is the orthogonal projection? What should be this length? This length is the time, so which would be the time. The length to the orthogonal projection, which would be what? It will be t0 in our case, will be q times 1, 0, which is dot product. It's x, y, dot product is 1, 0. Dot product is x times x plus y times 0, which leaves us with x. Which makes sense, because I just wanted the distance to the x coordinate. The distance from 0, 0 to the x coordinate. Now, if I actually want to generate this point, how can I generate this point? I'll take this scalar and multiply by the vector Vx, which will generate this point. It will tell you if you start your travel, your journey at 0, 0, then goes small x, scalar x, steps in the x direction, it will give you to this point. And now add to it some scalar times y, and you'll get to this point. Everybody's good? Again, it was a toy example, but it's a good toy example as far as understanding how we are working with time. OK, rendering, big word. Rendering is a task of taking three-dimensional scene and show it how it is seen to the user. OK, we can make images, photography or drawing. What are billboards? The billboard, the examples that I showed you before, with a background taken as an image, possibly. Is this closer to photography or closer to drawing, or this more graphical? Well, where I'm going with this, it's image-based rendering. It's a term, Google for it, or ChatGPT for it. Image-based rendering, it's a graphic scene that, including it, we are using pieces of real images, of real things. Very useful. OK, rendering, I can think about go over all the objects in my three-dimensional scene. I have my three-dimensional scene, what you'll get as a JSON file, list of billboards, list of files on each billboard, and list of spheres. Spheres that, by the way, look suspiciously similar to hot air balloons. And you're taking all of them and render them on the screen. So that's one way to render. Another way is image order, which will be for each pixel in the image, decide what is the color of this image. See the difference? Here, the main loop is for each object in your three geometric scene. See if it fits your screen at all. Maybe your camera is in the other direction, but if it is your viewpoint and it's the right direction, could it influence what you're rendering? But your main loop here is on the object. Your main loop in the image rendering, in the image order, is go for each pixel and shoot a ray through this pixel to tell me what you're going to draw on this pixel. OK, so each object, and now ask for each object. Does it affect the pixel? Here I'm going for each image of the pixel. And that's the idea of ray tracing or ray shooting. And what we are going to cover today and the next class of the Zoom will be the image ordering. OK, that will be go through every pixel. And by the way, it kind of fits into parallelization, this ray tracing, because what I can do here is that pixels are not depending on each other, so I can do the same operation for each pixel, which will push all the objects, which is essentially how the Z-buffer algorithm will work. Just go for all the pixels, possibly in parallel, depending on your hardware. So ray tracing, ray shooting. Here is my eye. Here is the image plane, what I'm going to render, pretending that my monitor is a transparent window. And here are the objects. And thinking about my eye as a point, it decides, it suggests some perspective of the object. OK, and I'll just, how do I generate it? For every pixel of my image, I'll shoot a ray through it and ask, hey, are you hitting a red cube? Then this pixel should be rendered red. Okay. So my eye shoot a ray through it in some direction, and I need to teach you how to generate all these rays. That was a bad wording. You need to study how to shoot these rays. I'll try to help. And you are generating this ray, and now you realize that this ray hits a blue sphere. Homework 3, you're happy with this, and you're just taking the color of the blue sphere and render it to the pixel that generated this image. Later homeworks, you will ask, hey, how much intensity happens right here? How the luminosity, how live is this? Is this pixel shaded, actually? That's the sun. A pixel right here will be in the shade, much less illuminated. A pixel that points to the sun will enjoy maximum intensity. There are some effects. Maybe there are more effects from the specular parts, shiny points that will appear over there. That all comes later, but they all start by, let's decide how much light is falling from here. How much light from this light source is falling on this point? And if my only light source point is the sun, then it's kind of easy. I'll hit this point, and now from this point, how do I know if this point, this part of the sphere, is shaded or not? It might be not the only sphere, so what do I do next? From this point, I want to draw a ray to the sun and see if this ray is blocked or not. If there is another sphere that blocks this ray, then it should be completely dark. If this ray is, if it sees the sun, then depending on the angle, I can accumulate the light that falls on it. But a ray from this point that it will try to get to the sun, of course, needs to go through this ball. So unless this ball is semi-transparent, if the ball is opaque, it will be completely in the dark. Except that it will not, right? We can see things in daylight, even though they are not directly illuminated by the light. We can see things underneath the chairs. I like this example in this room. We can see details underneath this chair, even though if I'll ask about this point just underneath each chair, it's not exposed directly to any of the lights around you. So how come there is light that falls on it? Well, because there will be light that falls from reflection from the walls, reflection from other objects around us. So it's not only one ray that I need to shoot from here to the sun, or to the only, also rays to any other sources of light, and other objects that are not sources of light by themselves, but could reflect light. So we'll play with this a bit more. So it's not only one ray, it's multiple rays, and when I hit the wall, if I shoot a ray from underneath the chair to the wall, well, or the whiteboard, well, it's transparent, but now is this part is occluded or is also in the shade of the light underneath this black wall? How do I know about it? From this point that I just hit the whiteboard, I need now to shoot another ray. And I'm not always sure to which direction, so it's multiple rays. So it's exponential in how many degrees of do I need to, how deep is the recursion, and how many rays in which direction do I need to shoot. All items that we'll explore much more in future part, where we see that we see a reflection in the floor, this big sphere over here, reflection of light that comes directly from the sun, or some bluish, because there are rays, that comes from the blue sphere. Not in homework 3, later on. Okay? And that's a difference between ray tracing versus ray shooting. Okay. So how many levels in the depth do we need to take, and how to generate rays in any reasonable way? I don't want exponential blow up. Okay. So we understood what is ray tracing. Ray shooting will be just one level. Homework 3, just one level of the recursion. Okay. So for every pixel, just to summarize what we just said, compute a viewing ray. How would I do it? I will have to find that in the JSON file, where is the camera located. I will pick the image plane that will be somewhere here, the screen of the window, screen of the display, of pixels. And for each one of them, I'll assign a point, which is a pixel. And now I shoot away from the eye, from the camera, pixel, and try to find out of all the spheres and all the billboards, what's this ray out of many, one per every pixel, what is the first object that this ray hits? And if there might be more spheres coming up, but if this sphere is blue, then I'll assign the pixel that is relevant to it to be blue. Okay. But again, there are more effects that you see over here, like the specular spots that will happen at the center of the ball, this tiny white part. You see different types of shadings underneath it. Things can become easily more complicated. Homework 3, only ambient light. Lights with no direction and that cannot be blocked. Nothing in shades in this homework. Okay. Compute for every pixel, compute the viewing ray, intersect the ray with the scene, and copy the color of the object at this point that you hit to this pixel. Okay. And if you do want to care about shades, homework 4 in part, but you want to start thinking about it because, well, we'll need to implement it from a point that build your ray shooting, your ray tracer, in a way that you can call it recursively. Once I hit a point, now I want to shoot another ray to the sun to see at which angle the light comes, and if at all. If it's on the, is it shaded by another object, or is it exposed to the light, and at which direction do I see the light? So build your ray tracer in a way that think about that you can call it recursively. Type of perspective, parallel projection, orthographic view versus a perspective view. Don't tell any news to anybody. Perspective view, where is the camera? To create orthographic view, camera is somewhere is infinity. All the rays from the camera are parallel to each other, shoot one way. And what did you do? You just project now the same projections that we had on the line, like orthogonal projection of the object to the camera screen. Orthographic, the camera has some distance that has distance less than infinity to the object, which means that even though it's a cube and edges or in 3D have the same length, edges that are further away are shorter. Right? Cube has the same length, but how do you know, hint about the 3D structure of this cube is because some edges are shorter than other edges. If I have two parallel lines in 3D worlds, will they appear parallel under orthographic projection? And then the same question, of course I was lying, that's a slide with orthographic. Sorry. Perspective, here is much closer, and then you can see that it's a bit exaggerated. Edges that are closer to the viewer are longer than edges that are further away. It was the wrong slide. People in perspective will parallel lines that are parallel in 3D. Is they appear parallel under perspective? No. Can they meet? Lines that though are not parallel, they meet. Example.
Funny, even in the diagram, do you imagine like
Mm-hmm.
they're meeting in front?
Yeah, It will take this image long enough, you see that this edge and this edge will meet somewhere. Good example, look at train track. Look at an image of the train track from a viewer that watched a train track and the two lines of the train track. Seems as they meet. Okay. While in, of course, orthographic projection, yeah, they stayed parallel, obviously. We are going to use something very similar to the pinhole camera, except that we are not reversing the image. Pinhole, it actually works. Try it out if you've never seen it. Take the object, draw the camera will just be symbolized by 1 point, and I take to know what is the color of this pixel, to know what is the color that will be rendered on this pixel. That's my display, what the color on this pixel. I'll shoot a ray from this pixel through the hole until I'll hit one of the objects, the cup of the Stanford teapot, and that's the color that will appear right here. Make sense? And I'll do it for each one of these pixels, and this hole has infinitely small size, and then it works. We'll do the same, except that now it's the viewer as an object, and the screen is somewhere in between. Yeah, it's very cool that this trick actually works. Try it. Okay. Now, pinhole camera will means here my object, camera location, image screen, and as we'll see, it's not critical where exactly we are putting the image screen as long as we are keeping the right proportions. There are various pixels. Through every pixel, shoot away until you hit a point. And that tells you what the color of this point. Defining array, origin, we know it. That was O1, and the direction, a vector. It's convenient where it's unit length, not crucial. Which direction it is? P at time t is the origin plus the vector d times the t, times t. Okay, that's parametric representation of the ray. P of 1, P at half, just the middle of the point between P of 1 and O. P of 1.5. Okay, that's T is a non-negative, it's negative, it goes opposite direction. And actually you're going to use negative or values of T. In your homework 3, you will definitely, sometimes happens, that T, it will turn out that T is negative and you want to know about it. You know why? Guess? You will shoot rays. You'll find where the ray intersect one of the spheres that I told you about, one of the balloons or one of the billboards. But it will turn out that it happens in t equal -3. What will it tell you? Would it tell you?
You have to compute where it's going to be at t0.
To render the image, I took the image plane, shoot a ray through this image plane, and ask where does this ray hit each one of the objects in this room. And it turns out that this ray hits an object at t equal -1.
You simply ignore the ray?
Sorry?
You ignore the ray that's behind you?
Not ignoring the ray. The ray is legit. The ray is legit, but you said it.
Because it's behind you, so you have to.
I don't ignore the ray, but I ignore this intersection point. At which time will this ray hit the whiteboard? When I'll do my math, this ray that I'm shooting in this direction will hit the whiteboard, but it will be negative t, meaning that the object is behind me definitely doesn't influence the pixel that I'm going to render right here. Okay, so negative t just means not relevant to this image. here's the image plane. Finally, we see it. There are a bunch of pixels, and what will determine the array will be the center of the pixels. If you want to be very uptight, and I will not be angry if you'll decide about, say, the lower left point of the pixel. That's also fine, as long as it's half a pixel error. How many pixels do I have on the x and y? That will be in the JSON file. What's the resolution of the image that you are creating? Okay, in the JSON file, part of the parameters that I'll tell you is where is the I, x, y, z. And I'll tell you something about the up vector. From the up vector and the array, and I'll also tell you what are you looking at, which will determine what is the direction of pixel 0, 0. Pixel 0, 0, that will be the center of the image plane. Going up and down, you'll control it by the v direction. V will go up and down, and u will go left and right. You will go left and right in the image plane. Does it necessarily, is the v direction always points to the, now it's not the z, because z we said is a depth. The image is x, y, z going in the depth, going behind me. Definitely not z. But does the, typical error is to think that v necessarily points to the positive y. But not necessarily, because I'll tell you what is the up vector. And the up vector might point vertically up, but as I said, if I want to do flight simulator and I want to rotate the camera, how do I tell you to take the camera in this angle? I'll tell you that the up direction go this way. Okay? So what the camera thinks as up is not necessarily what the x, y, z coordinates agrees with the up direction. But it's not a problem. Right will be controlled by another vector, u, going left and right. Here goes u toward me. Here goes v upward. And I need a third direction, which is w. Very tempting to think w is pointing to the center of the camera plane. Very tempting to think that w should point to the direction that we are looking at. But what's the problem with it? That I want u, v, w, the new coordinate system that I define, to agree with the xy plane, xyz. Sorry. I want it to agree with xyz. I want to be able sometimes to rotate it. So u, positive u becomes a positive x, positive y, positive v becomes positive y, and positive w should become the positive z. Now, u, v, w. What is w right here? It's going in the opposite direction. Why? Because what did we say about x, y, z? The same x, y, z that we all know and love. X, y, z. Right hand. U, v, right, up. Where do a screw that you put and rotate from u to v will go in w. If u cross v will be the vector w. That's how you generate w. Where do you want w to point? Not to the center of the image, to the opposite direction from the center of the image. Good source of confusion, undoubtedly. Okay, so stay with this image in mind. W points to the opposite direction from the direction to the image of the plane, and it comes from some good reasons. Want to agree with the x, y, z. Okay. Already have it. Object is a I, and I want to generate. I'll want to generate an array that goes through the pixel S. How can I generate this way? What is the array that goes from the I through the pixel S? Here it is. E, the I, plus t times what vector? Vector that goes from the pixel to the I. Vector that the pixel minus the I, vector that goes from the I to the pixel, the opposite direction. is this unit vector? Not necessarily. So when you're computing the intersection with other objects, either you normalize it by the length of this vector, or you'll decide that you replace this vector by a unit vector. Either way, you just need to be aware of it. It's not a hard problem, but if you don't think about it, it could be confusing. You'll get the wrong time. If the vector is twice as long, then t is half the time that it takes it to reach to some point. So S minus E, S is one of the pixels. S can be any of the pixels in the image plane. So you see what the, start to see what the flow will be. That will be how when I decide about the locations of all the pixels in the image plane, when I decide about all the pixels in the image plane, then I can start generating rays. And to generate rays, I always look at the vector from the eye to the pixel. OK. When, in this case, U goes from 0 to 1, V goes from 0 to 1. And in this example, I'm using I and J. And I'll take the middle of the pixel. So U, how much U do I need to take? It will be corresponds to which to generate. I want to map my image plane, continuous image plane that simplicity I parameterize by 0 to 1 and 0 to 1. That's the image plane. How do I map it into pixels in my image? Nx, how many horizontal pixels I have in a row, Nx, and Ny, how many pixels I have in each column. That's part of the input. You want higher resolution, increase Nx and Ny. Doesn't even have to be the same number, right? Your aspect ratio might be different, number of pixels. On X, number of pixels and Y. OK. What does this value gives me? That for every I, it tells me how much of U do I need to take, how much V do I need to take. I have a better slide to this part that tells you how much of each one should I have to take. So let's keep this. OK. Camera components. We'll get back to this point. Sorry. Camera components, and we'll call it a day. So I have to define a few things. I need to tell you where the camera is. I need to tell you what it is looking at. I need to tell you what is a field of view of the distance. Distance to the image plane. So what else? I need to tell you what is the up vector. Third time, up vector might be positive y, not necessarily. Why do I want to keep it separately? Again, because when my camera changes its orientation up, down, left, right, I still want not to update the up direction at the same time. What I'll give you is what is the angle of the field of view of the camera. What is the angle that you want the camera to have? Right? So zoom in and zoom out is nothing but changing alpha over here, changing how wide your watch is. If you're not changing the number of pixels, then of course decreasing alpha will mean the same, decreasing alpha meaning the same number of pixels is used for much smaller part of the image, implying, of course, zoom. If you want the image plane, and you'll see different schools about it, if you want the image plane to go from in the width between -1 and 1, and I told you what is alpha, then you know how far the image plane should be. It's called a plane, but it's only a rectangle. How far away the image plane should be from you. You want to compute D. D, which would be, think about it, tangents this divided by D, the distance that you want to compute. This divided by D is tangent of alpha half. So D is 1 over tangent half. That gives you the distance to the image plane. Now you need to start placing points on it, which will be the pixels, and then you can start shooting ray through each one of these points. That will be in the recording of next class, or next class if I'm being told. Questions here, ignoring the previous slide, about what is exactly x and y. It's very easy now to just say I'll uniformly spread pixel across these points. That would be the nx, and if ny is the same and alpha is the same, then it's obviously how I place points on the other direction. Just a bit algebra to play with. People, are you good? Sorry that I confused you with the previous slide. Perfect. Thank you. Question? Homework 2? Everybody is good? Okay. Again, Mills told me that he's almost